joined iTHEMS around in May, and today I'll be talking about scale transformations in physics and beyond. This is a topic tightly related, or basically about the renormalisation rule, which is a core central concept in theoretical physics. And already people have discussed this in previous coffee meetings, Masatsumi, Dongbuk, but I wanted to talk about this because I think it's very useful for very different areas beyond physics. And actually, that's the way I wanted to present it, in a very conceptual, non-technical way for those that are not familiar with. And yes, I hope with this, we somehow, maybe this appears as a concept where different areas can talk, and with this, we have some common ground. Very well. So I want to start by posing a question that is, how do the properties of a certain microscopic system emerges out of their most fundamental description? So for what I mean by this is, for example, let's think a system like a table. Table, we know, has certain properties, conducts electricity, heat in a certain manner, but we know it is an ensemble of many body probabilistic quanta, which additionally follows certain laws from some description, which works very well, but only at a very fundamental level, right? So very at the level of microphysics. So now the question is, how does the macroscopic properties of the table emerge out of the most fundamental description that we have of this system, that it's basically this one? So, and what we, to answer this question, what we need to do is to try to address what are how does the system, the microscopic description, behave along scale transformations. So, in fact, I think this is not only a physics, so this is not only a physics question, and it's common to many complex systems, statistical probabilistic systems. So, for example, in the context of the talk that we heard last week by Leo, we can think of the genome as a compound of nucleotides, which nowadays, the present modern genome is just the product of having evolved this statistical probabilistic system along the time of generations. So now, if we want to reconstruct the ancient genome, what we can do is try to take the fundamental pieces, understand how they give rise to the microscopic genome, and see with these scale transformations, see how it evolves also on time. I hope that this is a bit hard to grasp, but I think it's a way to go. Very well. So why I think it's interesting? First, it will let us understand what is the origin of the properties of a macroscopic system, and reconstruct the knowledge of this system. And if you think it the other way around, if you're a fundamentalist, you want to see how does this system in the microscopic limit appears. And in particular, this is very useful to use these techniques if you have emergent phenomena, such as, for example, when your system at the fundamental level or at the microscopic level has a very different description. For example, there are other effective degrees of freedoms like bound states, etc. And another point that I think makes interesting why to take care about this is because systems, when tuned into a particular critical configuration, can display are completely independent of the microphysical description, but only are their properties are only given by the statistical probabilistic nature. So this leads to some universal behavior. So this, in fact, allows to connect systems which are very different. So, for example, a tabletop condensed matter experiment with, for example, some birds flying or some type of cells. So yeah, this is a very powerful concept. So before getting into some kind of hard system, complex system, let me introduce how do these scale transformations come out in a very simple system that is the so-called iTHEMS model. So this is a two-dimensional surface of spins, which spins are just some magnetic dipoles that can be pointing upwards or downwards. And if they are upwards, we say +1, if otherwise -1. And this is a system in 2 dimensions in space, and we put it on a thermal bound. Okay. So now we can arrange at all the sides of the surface, the spins to point upwards or down. And with this, what we arrange is a configuration, a particular configuration that you change the different spin. Now, the energy of the particular configuration is given by the so-called action, which has the coupling between the nearest neighbors, the nearest neighbor spins, at a certain temperature. I will call this K, and now the sum over all the nearest neighbor pairs. Very well. So a very important quantity to describe this type of statistical system is the so-called partition function. And this partition function, basically what does is summing over all possible configurations of the system. And at the same time, weighting this sum over probabilistic sum over the action, over the microscopic description. So this quantity here is already non-trivial most of the time, because making the sum over such a large system, with different possibilities, we have plus or minus, may be a non-trivial task. And in fact, this object encodes all the thermodynamical statistical properties of the system. Very well. So now if we want to get an observable of the table, the only thing that we do is we take the respective operator and we put it in between the sum and the weight, and what we perform is the sum over all configurations. And we also normalize this by the partition function. So the catch now to resolve the system or get the properties is to perform this sum over configuration. All right, so in order for simplicity, let's consider that we only have one chain. Okay, so now the chain is given by the coupling and the temperature and the interaction between the first and the second spin, the second and the third and fourth, and so on. So now what we can do is decompose the first sum by the sum of the first and the second and the third. So collect the interactions only with the odd position spins. All right, and now we take the particular odd one, for example, the spin 2, and we sum over the two possible values that this spin can have, +1 and -1. This system is very easy. And in fact, what we get, and this basically gives this sum here. And now what you can do is actually, it can be shown that this sum here can be written as a function of the coupling times an exponential, which only encodes the product, the interaction between the spin 1 and spin 3, with another coupling, an updated coupling. This is very important. So now if you plug this back in and do this for all the odd spins, what you're left with is the partition function with a function of the coupling, and now the summation over the configurations of only the odd spin positions. But this is nothing than some function of the coupling and the partition function for half of the degrees, half of the spins of the spins. So what is this telling us, and this is important to understand, is that the description of the system has some kind of recurrence, some kind of scale transformation. Where is the scale transformation? The system with n spins is related to a change of the coupling to the system with 2n. All right? So now what we can think is that the system has the properties of the system for some correlation length L is related to the system that with correlation length L prime. Right? And what happens, the only thing, how is this transmitted, is with a change of the coupling. The fundamental interactions here change. Very well. So now let me just, so this is hard to understand at first, but I think more or less came through. So now let's see, for example, draw how does the coupling evolve as we take the infinite length correlation. So now we don't want to only know the information between two spins, but we want the table, right? The whole. So it's basically taking the correlating length, the correlation length, up to infinity. So now what you can see is if you solve it for the 2 plus 1 dimensional icing, is that the coupling can either go to 0, to infinity, and or there is a particular very special solution in which the coupling does not change. The coupling remains a scaling variable. When you perform the scale transformation, the system does not change at all. So this is, in fact, what you can do is there is an infrared fixed point. And this fixed point gives rise to a singularity in the partition function, which has a correspondence to a phase transition in the system. So now, for example, let's take an observable, such as the magnetization of the table. And what you can see is that this gives rise to a certain critical Curie temperature, which distinguishes the phases. So a phase in which the magnetization is non-zero, and there is some kind of spontaneous arrangement ordering of the spins, they're all aligned, or a regime in which they're all random. Okay, so this is all coming out of accounting for the microphysics and taking it to the continuum. And very specifically, the point which was given a phase transition is that of the critical temperature. We can take now an experiment and put it precisely at the critical temperature. And what we can know, what it has been shown by Wilson, is that the observables follow some kind of universal scaling at close to the critical regime. And in fact, now that they are described by some critical exponent, which is universal, independent of the microphysics. So this will be served by different systems. Very well. With this is pretty much what I wanted to say, and I just want to give one more note that this is an idea that was developed mostly in the 70s. How is this actually being done mostly now? So what we have normally is a sum over configurations that it's not so easy. It's not spin 1, spin plus 1, spin minus 1. But what we can have is that now the spins take a whole continuum of values. So now basically what you can, this configuration sum can be the product of each of the sides times the probability, a continuous probability of values from minus infinity to plus infinity. So this is in fact what happens if you have a toolkit. And this is now much more complicated if you want to sum over these objects. So in fact, what we do when we want to solve this is we write it in Fourier space, in momentum space, and sum over the different modes of the distribution. And this, in fact, is what it's called the functional integral or path integral, right? So this is a beast. So they're very hard to compute. So now another way, or the way that I like to do, is that it's an analogy to this coarse graining, taking average, accounting for the information in different lengths of scale. And how is this done? Is what I like to do is to define an object that is equivalent to the partition function, but only carries the information up to certain length scales. So this, what it's doing is basically accounting for all the information of the system down to certain length scale L, which is equivalent to certain momentum scale, right? And then for catch. So now, if you take the limit zk goes to 0, you recover the knowledge about all length scales, and you have the full description of the system at all energies. So how do you do this? So for it, you need to get your hands on some kind of equation that describes the evolution of this system, of the partition function over the energy scale. Very well. And this exists. This was, for example, equations put forward by Wilson, Wegner, Potwinski, and Wetterich. So with this, I think this is a formalism. It's very solid and very powerful. You can solve very complicated tasks. And in the last second, I want to mention what type of problems I'm considering, I'm worried, or I care about. No? So in fact, I deal with partition functions which describe nature at its most fundamental level, the best, and excluding gravity. So for this, what we do is I care about partition functions that carry all the information about all the matter content and all the forces known to exist in nature, except of gravity, I would sometimes put it. And what we learn, what I care, is to see how the system behaves as we look at different landscapes. So, for example, in this action, what I include is all the forces in nature. So the strong force, the weak force, or the electromagnetism. And what you can see is, for example, that the nuclear force becomes weaker and weaker as you go to shorter and shorter length scales. And or for example, electromagnetism becomes stronger and stronger if you go to shorter list. And also there are some peculiarities if you see how, for example, the Higgs boson interacts with itself. So my concern is to study this object and the phase structure similarly to what we have seen here, and see which modifications of the standard model you can make, or our fundamental understanding of nature, in order to solve the open problems in puzzles that this fundamental understanding currently has. That is, for example, what are the origin of scales, where does dark matter come from, and so on. So thank you very much.
Okay, thank you, Álvaro. So, past questions from non-experts. Yeah.
Sorry, I think it's more question on the physics model in the end. But in what sense you're explaining this universal? Because you talked a lot at the beginning about universality, but in the end, the computation here, if I'm a bit mean, it's just for the physics model. So what is universal?
Yeah, good. Thank you. So it's very, very good, but yeah, very, very good point. So I mean, what you define what the point is that this critical exponent mu will appear when you study systems which are within the universality class of this Ising model, for example, in 2 dimensions. So
Universality class.
yes, but I mean, what I mean is like you can find within this universality class, for example, the behavior of soft matter systems. And I mean, you can do very similar things for the description of some kind of biological system, as this has been shown. There is plenty of work. And you show that, for example, the change of the system behaves in the same way within the critical, close to criticality, so where there is a phase transition.
Isn't the tricritical point of water in the universal class of Ising as well?
I think I'm not on top of my head, but perfect, thank you.
It is.
So, for example, this is a model that describes layers of copper and zinc, but as well the phase transitions of water. So there are very different microscopic definition. And I mean, I actually look at some other system farther away from physics, but doesn't come out on the top of my head. But in Wikipedia.
But a critical point in the past order phase transition, therefore I think it's not needed.
No, it's not.
Yeah.
Sorry, but I mean, so it's actually an important point to stress that this parameter here does not depend on this action. And this action is the microscopic. So how do you describe the system at its most fundamental level? But you can have a completely different system, like a system of birds that suddenly start flying. So I say this because I know there has been some studies here.
Phase transition is always the same.
Yeah, but this is for second order phase transitions. Yes, absolutely. Yes. Which are very special. But
Yeah.
so
Yeah.
I don't know whether it's a sensible question. So you said that the emergent property is highly related to this critical behavior in the phase diagram. My question is, how can you guarantee that in your generalized young standard model partition function, that kind of critical behavior always exists?
Good point. I mean, I'm not looking precisely for the critical. I mean, I'm not looking in order to deform the standard model in such a way that you put it in some kind of fixed point that it's given by this. But I mean, in fact, we know this cannot be the case, because if you go to some kind of fixed point like this, you would see that your nature would not change as we go to different landscapes. And I mean, we know, we measure that nature changes. It might be that there are some kind of fixed point that this redeems, and then this is related to conformal invariance, and then somehow you are slightly deviated from there. But I'm not trying to understand, put the standard model with new physics on the fixed point, but I want to understand where the fixed point of the standard model is. Because I mean, that one is, you can ask yourself, why are we in this position within this very particular theory? So, for example, if you take the analog of this system to the standard model of particle physics, what you know is that you're living very, very, very close to the scale invariant theory, and this, but not on the scale invariant theory. Now you can ask yourself, why are you at this particular distance from the scale invariant theory? And this maybe is provided, an answer to this question, by some kind of deformation or some kind of dynamics that it's not apparent. Yes.
Got a very fundamental question here. So, in your calculation for the Ising model, where is the scale up here? So I didn't quite follow what parameter here corresponds to a scale.
Yeah.
And then the second question is, so you have phase transition. So usually you have to vary some parameter like the temperature or something like that. Like, so what is the temperature here?
Sorry, yes, I said it. It's very small written here. So first of all, the catch is that this is a good point. Here I defined alpha of t as k, and here what I'm looking is, this is some kind of dimension-full parameter. Okay. So now the question is, what is changing here, the temperature or the coupling? So I think you can see it in different ways. But anyways, so this fixed point remains if you look only at the coupling.
So is that alpha or kappa?
Alpha.
Oh, it's alpha.
Well, usually in
Towards
energy
alpha?
physics, we refer the temperature is a macroscopic parameter, and a coupling is, for example, what tells you how strong. I mean, this parameter in the actual model can be -1, +1, positive or negative, and this will describe whether you have a paramagnetic or electric system, I think. And but the point is that how it changes.
And so where's the transformation path?
Yeah, so this is a very good point. So now I just did some algebra, and I just rewrote the partition function for summing over all possible sides as the partition function over half of the sides, half of the number of sides. Yeah. Okay. So what it's telling you is that this system here, it's related to the system with double the degrees of freedom. So now what it's saying is, like, the description of this system, it's related to the description of this system with a transformation in the couplings. Okay. So now what you're doing is, what you can see is that taking what you care at the end is looking at all the effects, right? Because when you look at the whole table, you're looking over everything. Not only at the interaction between 2 spins, 3, 4 spins, but you're looking at the information over all the spins. Yeah. So the relation between the system of this length and the system with double of the degrees of freedom has a scale transformation within.
So it's the idea you would repeat the scale transformation many times.
Absolutely.
To get a macroscopic.
Absolutely. So what you can do now is, for example, you can derive an equation So now this is very bad. But let's say something like minus the length of the coupling of your theory. So this would describe how does the coupling strength of your theory evolve as you start coarse graining away.
And so the universality thing is like, so here you have the size of the system in every rescaling step. So is that then related to nu, or?
It's then related, the point is that now you look at how this thing scales with how the coupling rescales as we changes as we rescale the size of the system, and there is a particular solution that does not scale, that does not change at all.
Right.
So as you start zooming out, you see that the system is a scale invariant.
So
The properties of the system remain completely untouched.
So how does nu know? So you said there are these universality classes. So what property of the system determines nu? Or is this just something that comes out mathematically?
It comes out when you study the correlations given by this type of scaling in the near critical regime.
But like, does nu tell us anything about the physical properties of the system?
Yes. So in my opinion, yes. But it does not tell you about the properties of the particular microscopic description. So whether you put here a 4, 1/10 or whatever, but it tells you about the statistical probabilistic properties of the system. The definition of this point is that it's invariant under. It's not dependent on the microphysics. So what can it be? It can be that it's only so if it's not depends on the microphysics, it has to be that it's something depending on over the sum of the configurations, and the configurations are telling you about the statistical arrangement of the theory.
Thank you.
It's a slightly related question. So when you do this coarse graining or zooming out for the parameters, is there anything known about the convergence behavior? Because there's nothing which I can see at the moment which tells me that it should be like regular or monotonic. So
it depends. I mean, it depends on what is, for example, this function. So this is what you need to compute, right?
This one you don't know analytically, I guess.
Yeah, you can. Yeah. So for example, here we know many things. Here you can derive analytically, and I mean you may have in fact, here I have described a system which only has one parameter, so one coupling, and maybe you have a system that has different degrees of freedom, like in bosons, fermions, which are different type of particles, and they may couple differently between different sectors. Then you can see how this intertwined system scales. And in this case, what you will see is that, well, the bosonic and the fermionic interactions may scale different, and they may have some interactions, some interplays in which these fixed points appear more non-trivial. So at the end of the day, the whole question reduces to deriving, let's say, the RG equations for the flow equations for the cathode. And this thing will tell you how the system evolves depending on the boundary conditions that you give. Whether you put your system here, there.
Okay. So when you see, for example, it diverges in some kind of way, you know that it will never come back actually. Can you know this?
It depends. I mean, when you are far away from, so the way of how this flow works is very dependent on the system. But there are some crazy systems. So you have systems that are like the Lorentz attractor and so on, so kind of chaotic even. So this you can find very different microphysics descriptions that give you very rich landscape of RG flows. In fact, this theory here has 20 free parameters. So you need to derive 20 different independent differential equations which are for the RG flow of this. And of course, you can imagine that you move in a 20-dimensional, you have a flow diagram in 20 dimensions. So you will find very exotic structures. You mentioned that you could to use phase transition temperature using this. So can you explicitly write down some kind of model for some material so that you can see that the temperature matches normal? So in physics, we only measure relative quantities. So a temperature, we can say that there is a critical temperature when you do a theoretical computation, but then to say that this is 20 whatever potatoes, you need to have a reference scale. So if you have a system with multiple scales, you can relate the scales. So for instance, I don't know, you have 3 different materials and you can relate to them other and see the temperatures of I don't know, the relation between the temperatures corresponds. In principle, yes. I mean, if you have, for example, like an effective description, let's imagine that I have 3 different materials that I can describe with the same action, but different parameters. Different critical temperature, different materials will appear as different configuration of parameters in this action. And in this model, the different materials have different alphas, or also some other parameters. Yes, only alphas. I mean, yes. So, I mean, I was just to your question, just to clarify, you could perfectly measure, say, the relative temperatures, but the absolute one you need to measure.
Yeah. Okay, I think you are an expert.
I have a question. So in your bottom line relating to partition functions of different scale, it seems that when I take n to infinity, then it seems that I get a equation for the partition function of the 1D Ising model. And in principle, you can solve this. Oh.
Yeah. So if your question asking if you can solve this.
Yeah, if I can take n to infinity.
In particular, the one-dimensional Ising model was even solved before Kalanov, but I don't remember the name. Maybe. And so these are so in particular this action is solved.
Yeah,
and
so
I think even exactly
can you see how to interpret your scale transformation in terms of this whole 1D Ising model when you do not have a concept of half of the bins?
Yeah, I mean, if you have a chain, you're looking again, like the table is the whole chain. You have this interaction, these interactions, and then you relate this to a system of this size, to a system of that size. I would see it like that. More like you have a chain. Yes. And then you break it into subsystems. And then you see how does this scale with the size of the subsystems.
So in this sense, you can somehow understand the microscopic phenomena in terms of very small pieces.
Absolutely. So this is the whole cut, fundamental microscopic spins to see how, for example, it behaves the properties of the macroscopic metal that you're looking. So what you observe is the whole ensemble, right, of many bodies. And the question is, how does this from very similar descriptions go to different properties of different energies? But thanks.
Yeah, number 5.
Okay, so this example is a quantum mechanical example. Did you research considering like a pure theoretical chain, especially in the context limit and something like the standard model that was takes what is the difficulty? Or is it straightforward, or is it the biggest difficulty in your opinion?
So this is pretty much statistical. If you take really a quantum field theory, so there are some quantum field theories that are exactly solvable, but when you really want to look at actual systems like the standard model, one of the main challenges is that these things, you may have strongly coupled physics or non-perturbative physics, which cannot be solved in the most naive approximation of perturbation theory. These are the ones, for example, where it's happening in QCD. So in fact, what is the main challenge is to describe really the dynamical phenomena that are happening in an accurate and controlled manner. So at the technical level, is how to solve this thing non-perturbatively. Not to say exactly, of course. I mean, ideally we solve these things exactly, but as in most systems in the universe, you cannot solve it exactly. I'm happy with non-perturbative systematic approaches.
Yeah, so questions from anybody? Yes?
So I'm a little bit confused with so on the one hand, you said you want to understand the macroscopic phenomena from the fundamental description. Now, on the other hand, you said something like at a certain point, the property is really irrelevant of the detailed descriptions or whatever. So,
But thank you very much, because that's a really great question. Because I mean, the catch is that you may if you take, for example, the standard model, and you really look at the microphysics description, you can actually look at a macroscopic system and see the same properties. So, for example, if you now take the standard model, the universe, put it in a box and start heating it up, what you will see is that the behavior of the universe is undoing physical parameter like a temperature undoes quantum corrections. So understanding the microphysics is also understanding the properties of the macroscopic system. This is a very important, I think a very important point, because now you see, like, this is not really looking into the past, but looking into the future, like the whole, let's say, properties of the microscopic system, but from the building blocks. And I think this is in particular relevant if you want to look at biological systems, because the way that, for example, the nucleotides may interact will become relevant when you take different scale transformations, when there are few nucleotide interactions. So understanding the fundamental, it will also it will manifest when you take certain limit of the properties of the macroscopic limit.
Right, but in general, there are some limitations, right? You cannot understand all macroscopic properties only based on the very fundamental descriptions. What are the limitations?
I mean, so what so the limitations is, for example, that we live in a world that also has, let's say, real-time dynamics. That the systems, I mean, you can have very good understanding of the fundamental description, but you need to put on top of that the behavior of, let's say, your fields or your theory, as you have a real-time system, a dynamical system evolving in time. Yes.
Any other? Yeah.
So you've been quite quiet about gravity. What kind of challenges is gravity pose for?
Yeah. Well, maybe you tell me. So I'm actually. So what do the challenges? So gravity. What I'm saying here, gravity, is because here this is a diagram of the strength of the fundamental forces as a function of the length scale. So, for example, going at a large case is going to very short distances. You're showing the interactions between the fundamental particles. But at some point here, what you expect is that quantum fluctuations of gravity, so the dynamics of the metric, the space-time metric, actually become relevant. So, where do I start? So, I mean, that you're concerned about the metric, about the measure, but I mean, So to solve, so gravity, it's inherently non-perturbative, which means that in order to find a description to solve how does this behave in scale, you really need to use advanced methods. And I mean, there are some interesting solutions when you do this formalism for gravity that find that gravity can scale in the Transplanckian regime. And this is a very path integral partition function, let's say, picture, quantum field theoretical picture of gravity. But I mean, where do we start? Is this the correct formulation? Is this well defined?
But I think a good point for normalization group is that even we don't have a knowledge on very high energy physics or very microscopic theory. We can have some guess from the low energy to a bit higher energy.
Absolutely.
Yeah. So
the renormalisation group allows you to connect the physics of different scales. This is very important. And then, in fact, this is what the reason why we know this works very well, this standard model, is because we have measured it at very different energy scales, and we have seen that there is a high precision. Now, in the context of gravity, this is particularly interesting because you can now see whether the matter can tell you something about its compatibility to gravity. So this is one of the, for example, features of asymptotic safety in interplay with matter, and the ability of telling you what is allowed and what is not allowed.
Any other questions? Yeah.
Yeah, thanks. Maybe like it's very unlike to say about this. But as you mentioned, like this is applicable for equilibrium systems. Yeah. Is there any chance, because you also mentioned nucleotides and the evolution of DNA on long time. So this is a time evolution problem. Yes. More of an equilibrium problem. So my question would be, can you leverage these tools to rather discuss out of equilibrium long time dynamics rather than equilibrium scale dynamics, and thinking by, for example, of looking at the thermalization of the system?
Absolutely. So I mean, I say this is a very, very interesting question. I'm very interested in this because when you develop this picture, you make a lot of approximations, like you assume thermal equilibrium, you assume homogeneous distribution of your probabilistic distributions. But now the question is, can you actually do this for a system out of equilibrium, a system with actual dynamics? And there are some equations here that can work, but as long time evolution is really a challenge. It's really a challenge. And I mean, in particular, I think this is a very interesting question also in the context of fundamental physics and cosmology, because there are some theories which change as the dynamics of macroscopic systems evolve. So imagine that you now have a macroscopic system, like an inflaton having some dynamics, and as this inflaton or as this dynamics change, it will change your quantum dynamics. So there are techniques, but there are techniques, but nothing works perfectly. But it's a topic of research. And
any other questions?
Well,
From Zoom. Yeah.
From the
Physical
very naive question, you see. The other day, Dr. Onguri was saying that non-Wilsonian picture of gravity. And my question is that in the superstring, for example, everything is finite. Then, maybe everything becomes non-Wilsonian. So, that picture is correct or not correct?
That's a good question. Yes, so I mean, I have no clue, but I think also no one knows whether what happens at the Planck scale, it can be Wilsonian or not Wilsonian. I think I agree with what you're saying. There might be, I mean, the Wilsonian idea constructs on the fact that you can account for these quantum fluctuations in a progressive manner. And I mean, it might be that there is some interactions and some interplay between macro and micro physics here. For example, black holes interacting with gravitons, which many people have proposed actually and discussed. It's hard to deal with in the Wilsonian idea. Not saying impossible, but it's hard. Thank you.
Okay, thank you.
Any other question? Well, can I ask one philosophical question? Well, yeah, so universality is the holy grail for physicists. And so renormalization group is one way to explain why there is an universality in our nature. And for biologists, I think diversity is your holy grail. I'm not sure. So my question is there any universality in diversity?
So, I mean, in physics,
yeah, so suppose that there is life on other planet, then the diversity of the life there is similar to the diversity on Earth.
But that could be. That could be because how I don't know, but I would be very curious. How would you see some kind of critical phenomena in the evolutionary trees?
This would be but sometimes that occurs emergent. Yeah, so.
But it tells you that certain patterns will occur in the same way that Cooper pairs appear.
Because I have no idea, but maybe.
Well, I guess there is some universality in that if you're more diverse, you can more easily adapt to new environments. So I guess so that is kind of almost the whole point of.
So the more the better.
Yeah. But then at the same time, you kind of want to be optimal, which reduces diversity. So I guess it's that full, like that sort of balance of forces. So yeah, maybe.
Yeah, because the evolutionary dynamics is, in a sense, it's a very simple equation. So I'm wondering whether there is some very universal behavior from that. That is my.
I mean, I guess animals. Like the levels of diversity are very different between different animals for various reasons.
Okay, sorry, maybe nothing to do with your talk, but yeah. Okay, so any other questions or comment? Okay, thank you very much.